All right, so today we're going to talk more about contrasts. Yesterday we ended up only going about 30 minutes of the stuff at the beginning and then spent the second half working on the in-lab problem. So to start out with this first data set, we're going to say researchers are interested in examining the effects of 4 different antidepressant drugs. There's 2 newer drugs that are SSRIs and then 2 older drugs, the tricyclics and the MAOIs. Now, the way that they test these is they give them to rats and then drop them in a bucket of water. And then the dependent variable is how long do the rats swim in the water before they give up. And though that seems like it's not very face valid, it's actually shown to be quite predictive of how antidepressants work, the efficacy in humans. So we had these 4 different drugs, and we want to compare if the 2 SSRIs are better than the 2 older drugs, and then comparing the 2 SSRIs to each other and the 2 older drugs to each other. So we have our first thing is we need to set up our contrasts. So we're going to cover a couple different new ways of doing it this week instead of using a bunch of if-else statements, ways that are especially beneficial when you do have multiple levels. If you only have 3, and so one if-else statement, you only need 2 values, then it's easy enough, and why not go ahead and do that? One way to do it is using car recode. So all we're going to do is we're going to tell it for the group, for if it's group 1, make it -5. If it's group 2, make it -0.5, excuse me. If it's group 3, make it 0.5. If it's group 4, make it 0.5. And store that as C1. And I do want to point out, just to make sure, notice that there's only one set of quotation marks, and each recode is separated by a semicolon, not quote 1 equals -0.5, close quote, comma, the next set of quotations. It's all in one quotation there. So then we're going to do the same thing for C2 and C3. So now we've made these 3 contrasts. There's also, in the LM support package, there is a function called bar contrasts. And this has some benefits. But for one, throughout this, I use different naming things. Like here, I'm converting the group to a factor, and I'm changing it to group F. You could just factorize group and keep it as group and not create a new variable. The reason that I'm keeping them different names is specifically so as we work through this and we're working on different parts and looking at different outputs, we can keep track of what is coming from where. For instance, later when I label them C1, C2, and C3, that's just so that when you look at an output, you know the difference between this contrast versus the ones that are labeled as the letter C1, C2, C3, etc. Down below, I add some like C.1, C.2. Again, all that is strictly so that as we work through it, you can keep track of what's coming from where, basically. So just throwing that out there. So I make this factorized version of group and call it group.f. Now, by default, if we look at the contrasts, R will handle factors. It'll just dummy code them automatically. So what this means, when you look at this contrast, you see that the first group is a set of zeros. That's the reference group. Whenever it's dummy coded like this, essentially what you do is you leave out one of the groups. Like, you don't make any comparisons about that group. And in this case, this contrast will compare the mean of group 2 against the mean of all the others. This one is the mean of group 3 against the mean of all the others. And this one's the mean of group 4 against the mean of all others. But that's not what we're wanting to do. We're wanting to specify a different contrast. So I'm going to make this list of contrasts, same thing that we specified up here, just doing it a different way. So we make this list of lists, and I'm just calling it POCs. And then we're going to use this var contrasts. Now, a few things about this. Like I said, the C1, C2, C3, just to keep track of what's what. instead of making that list up above and making it an object called POCs, you could just put that list straight into here. You don't have to do that. The labels are optional. It just helps on your output because it'll say whatever you put in here is what your regression output will label it as. So it'll say group.FC1, group.FC2. You could label this, you know, the labels be 1 and 2, V3 and 4, and this one be 3V4, and this one be 2V4, and then it would say group.F 1 and 2, V3 and 4, or whatever the case is. As far as var contrast and the arguments that go into it, the POC list and the labels only apply when your type is POC. That's planned orthogonal contrast. So if you're doing, if type equals dummy, if you wanted to dummy code your variables, or Helmer if you're wanting to do Helmer coding, or effect, or effects if you want effects coding, whatever, you won't use those POC and labels thing. For instance, if you're dummy coding, and say like group 3 was our reference group, or what we were wanting as our reference group, if you tell it type equals dummy, ref level equals 3, then instead it'll make 3 all zeros and adjust the other ones as necessary. If you're using Helmer coding, ref level equals 1 means that you're reversing what that Helmer coding scheme does, which we'll talk about Helmer coding here in a little bit. The point is, when we set this up, if we run this line, we now have our contrast per group. You can see that it's put in our coding scheme and our labels. And so now if we just run contrast for group F, just as we did before, instead of getting dummy coded like this, it actually has our contrast in there. So now if we just put that factor directly into LM, it will use those contrasts. There's another function from the LM support package called var regressors. And what this will do, it will take whatever contrast you have in it. So if you haven't changed anything, again, it automatically dummy codes by default. In this case, we've changed our contrast, so it'll use whatever contrast you've assigned to a factor. And you tell it your data frame, what factor you're wanting to use, and then what to label your contrast. And what var regressors will do is it will create new columns for you. The way that before we manually created C1, C2, and C3, when you use var regressors, it will create C.1 as a column, C.2 as a column, C.3 as a column. So whenever we run this, and then look in our data frame, you can see we have the C1, C2, and C3 that we made earlier. And then here's the C.1, C.2, C.3. So if you, in front of this, if you put the assignment arrow and drugs, then it will store those 3 new columns onto your data frame. So it's just another way, if you want the numeric way of doing things instead of having that factor, this is a function that you can use to do that. One thing I forgot to mention yesterday, but I did mention in a footnote on the drill, is that one of the nice things about var regressors is that it will automatically unit weight these columns as it puts it out. So, you know, recall from lecture where we talked about if you need to unit weight, then you just take, you know, you divide by the difference of the min and the max. But this will automatically take care of it for you. If we needed to, if we had more levels or whatever, it would break it down into, say, like, you know, 0.8 and -0.2, -0.2, -0.2, -0.2. So we're still 1 unit apart, split on either side of 0, etc. So this will unit weight your things for you.
Quick question.
Mm-hmm.
So there where it has group F,
Mm-hmm.
you've already created your group F contrast codes through the POCs object and then through the var contrast function, correct?
Yeah.
Now it knows what to apply to those C.1.
Right. So I didn't run this right here where I changed the contrast, whereas before when I initially ran it right after I created the factor, if I did var regressors right here, then it would just use dummy codes instead of those contrasts that we put in. It just takes whatever the underlying contrast is, which is by default dummy coding, and uses that to create new columns. So to set up your contrast, you can use var contrast, recode, you can use nested if else statements, you can use whatever you want. There are some benefits to some versus others, but which is best for your particular situation can depend on the nature of your data, on the nature of what you're trying to do. So I'm just throwing out different options. You can do whatever you're comfortable with. It's just a matter of preference in a lot of ways. So now when we look at our actual models, I'm creating two models here, just M1 and M1X. The only difference is on M1, I'm using C1, C2, and C3. In M1X, I'm just regressing it on group.f, which remember is the one that we changed the contrast to. So like if we change this to the original group variable, you know, we would have a dummy coded instead of a contrast coded scheme going on. But when we look at these two things, we see that, you know, they're identical. The only thing that's different in these outputs is what the labels are called, where this says, you know, C1, C2, and C3, and this, like I said, group F, C1, group F, C2, group F, C3. So when we're looking at this output, remember that your intercept here is what? It's the mean of all four group means, right? Now, I'm going to go ahead and throw up the plot.
Was that time in the water?
Yeah, time, the amount of time that they spent swimming. Now, as far as interpreting this, we see that that first contrast, C1, is significant. The average of group 1 and 2 is significantly higher than the average of group 3 and 4. And then when we compare the differences between group 1 and group 2 and group 3 and group 4, those are not significantly different. Now, as far as how, if you need to get the actual values here of these group means, can anyone take a guess at how from this you would be able to figure out what each group's mean is? All right, so we start with the mean of all four group means, 74.3. Now, when we look at this output, it's this value right here. What is this slope right here? What does that tell us? 29.5.
So you're looking at the difference between the means of group 1 and 2 compared to 3 and 4.
Right, so the mean of these two, the mean up here versus the mean down here, is 29.5 points apart. Because these are equally sized groups, logically, if this is the midpoint between the average of these two and the average of these two, and this right here is the difference between this group and this group, if you split that 29.5, let's just call it 30. If you split that 30 and you go 15 above this line, you'll be at the mean of these two groups. And then you go 15 below this line and you're at the mean of these two groups. So in other words, if you split this right here and add it to this value and subtract it from this value, you now have the mean of this group and the mean of this group. So now imagine that we have, a line here and a line here. And we have these two values, which are the difference between these two groups or the difference between these two groups. So if it's 74 and we go up by 15, 89, we'll say the average of this group is 89, and the difference between those two groups is, which way did we code that? Is it?
I think it's the opposite. C2 is the 3 and 4.
Right. All right. So in that case, if this one is 89 is the average, and they're 1.5 points apart, again, you go up by 3/4 and down by 3/4, and you'll know that this one is 89 3/4, and this one is 88 1/4. Again, splitting that difference, and that's how you're able to figure out and work through to see like what are these actual group means and how you interpret what these slopes mean. Is everybody tracking on that portion?
Yeah. Did you write that down here somewhere?
No. Now, for a compact model, we want to look at just C1, that focal contrast. And just as a quick refresher, if you need effect sizes, model effect sizes, confidence intervals is just confident. And you can get those confidence intervals, some of those things, just to kind of refresh in your mind and remember what these different functions are that you'll need to use. But anyway, so when we look at the effect sizes of Model 1 and Model 2, notice that your R squared for C1 doesn't change. Furthermore, if you compare these two models using model compare, you'll notice that the delta R squared here is the sum of the change in R squared from C2 and C3. But again, that C1 doesn't change. Now, why is that? Why doesn't C1 change whether or not you add C2 and C3 are in there or not?
It's not accounting for a significant amount of additional variance.
Well, that's correct as far as doing the model comparison, but as far as why this number doesn't change, that's what orthogonality gets you. Orthogonal means that they are uncorrelated, they are unrelated. If they were correlated, then that means that they share some variance there. The way that it's computed, there is shared variance. But when they are completely unrelated, you can imagine that, I'll put it this way, if these weren't orthogonal, if C2 and C3 were related to C1, once you put those two in there, it's going to drop C1 a little bit because part of that is explained by these other things. But because they're orthogonal, they are completely unrelated, zero correlation, adding those additional things doesn't change how much variance that focal contrast explains.
Can you test to see if these things are like not correlated before you bother running everything? Like, can you do it if they are correlated a little bit because then it's not?
Well, I mean, it depends on what the goal of the analysis is. Kind of like whether or not things need to be unit weighted. As far as checking the correlations, all you got to do is run, which is what we're about to do, just run correlations on, C1, C2, C3, and we can see that, yep, they are all uncorrelated.
I just think if they weren't uncorrelated, like, does it mess up like the assumption of the test? You can't say that it's like a good test.
Not necessarily. It may change your interpretations of things, but you're not only allowed to do orthogonal contrast. And in fact, when it comes to orthogonal contrast, there's a finite number of contrasts that you can possibly do. Like there's only so many ways that you can create this orthogonal contrast matrix. Don't quote me on this, but I think that if you have like 3 levels, there's only 2 possible coding schemes that are orthogonal. If you have 3 levels, there's only 4 possible. And of each, depending on whether you have like 3 levels, 4 levels, 5 levels, there's 2, 3, or 4 ways of doing an orthogonal contrast matrix. And there's one way that's like the Helmert coding scheme. A Helmert coding is orthogonal. And then, but so like if you know, or just look up those like orthogonal contrast matrices, like, you know, there you have it. And you don't need to worry about, you know, figuring it out, which can kind of be a pain if you just start out by thinking like, okay, I need to make an orthogonal contrast here. But what that orthogonality means is that the sum of the products is 0. So when you look at your contrast matrix, if you take the products of each of these contrasts and then sum across the products of the 3 contrasts, that'll be 0. Or you can just check the correlations and get what you're looking for. Does that make sense? Cool. So we covered that. All right, so for the plotting, there's nothing new here. Almost nothing new here, just using ggpredict like we've done before. Notice that I'm putting the factor model in here so that I want this to be treated as a factor instead of numeric on the x-axis. Because in this particular case, it's just easier to do it that way. But I had to wrap ggpredict into as a data frame, because if I just stored ggpredict as plotdf, then it stores it as a list instead of as a data frame, and then it's not usable. But one thing, because this is the factorized version, you'll recall that whenever we've used ggpredict before, you know, it just defaults, it names things X and group and facet, and, you know, has that standard comp5, comp-flow predicted, always uses those same column names. But when you use a factored model, instead it labels the columns by the factor name. So it'll be like group.f.x, group.x.predicted, or group.f.predicted. So I did want to point that out, that this is what our column names are now when you use that factored thing. So if you're like, you know, just used to using predicted comp high and comp low, and you're like, why isn't this plot working? Well, that's because this changed the names of the columns by default.
Really quick before we move on, use the data frame function there, because otherwise it'll sort as a list.
Yeah, if we just run ggpredict, it has it as a list, not as a data frame. So you could do ggpredict, and then as I just did, ASDF, and then say data frame ASDF, or you can just wrap ggpredict in data frame and take care of it in one step. And then there's nothing new here. We just tell it ggplot, geom_jitter. Our X, we want the group.f. Y, we want our dv. For our points and error bars, we're using that plotdf and telling it, you know, our X is group.f.x, and then plus 0.3 just to offset them a little bit. Same thing down here, so nothing else there is new. You can do a lot as far as like how you want to represent these. We're not going to get into too much today, but for instance, you could do like make these dots blue and these red, and then you could reference that chart to say like, you know, contrast 1, the focal contrast compares the 2 sets of blue dots against the 2 sets of red dots. Contrast 2 compares the difference in the 2 sets of blue dots. Contrast 3, the 2 sets of red dots, blah, blah, blah. Or like here, I just added some lines, these geom segments, where you tell it like where X starts and ends and where Y starts and ends and what color you want it. And so I was able to just tell it, like put lines here. So now you could say, you know, C1 compares the average of these two groups versus the average of these two groups. And then I reverse that C2 and C3 label. But you get the point. Like there's a lot of different ways that you could represent this just depending on your preferences and what's important to you to have there visually. Now, any questions? Okay, so there are a few built-in contrast functions. This CONTR period is just contrast. So Helmert contrast, polynomial sum contrast, and treatment contrast is what it's called here. The 4 next to it, this just how many groups are there that you're wanting to create contrast for. So if you have 4 groups and you want polynomial contrasts, there you have it. So you could take this and just say contrast, you know, df, whatever your variable is, and it would then store this polynomial contrast thing as the contrast for that variable. What they call sum contrasts. Some people you may hear called effects coding. What they call treatment coding is just dummy coding. You'll notice that that's the exact same as the default coding scheme. Now, so when you're looking at the difference between these two, who can tell me what the difference is between this coding scheme and this one? What comparison is being made, or how would you broadly summarize the type of comparisons between this sum contrast versus treatment contrast, as they call it?
So you're seeing it on the treatment one, you're seeing if one of those levels is different from the other 3, right? And the sum one, you're comparing 2 levels to each other.
Right. More specifically, you're comparing each level to the same specific other one. So where this one, you compare group 2 to the average of all the others, group 3 to the average of all the others, group 4 to the average of all the others. And this one, you're comparing group 1 to group 4, group 2 to group 4, and group 3 to group 4. So again, it just depends on what the question is that you're trying to answer as far as which one would be most appropriate. Then I also want to talk about this Helmert coding. So when we look at Helmert coding, what that means is it's comparing, it starts with one level and compares it to each of the successive levels of things. So basically, here you're comparing group 4 to the average of groups 1 through 3. Here it's 3 to the average of groups 2 and 1, and here it's group 2 to 1. As far as, and you can also do reverse Helmert, where it's just going to flip those contrasts around and do, you know, each thing that precedes it. So as far as why this might be useful, last semester I gave a lecture. I covered an undergrad stats lecture for Build, and we were talking about follow-up tests to the Omnibus ANOVA, and the only thing that we covered was Tukey's HSD. So going back to the undergrad stats level, where like you come up with this thing and then you compare each set of means, 26 to 17, 26 to 10, and then you work your way and compare this one to this one, and this one to this one, and this one to this one. Each one of those comparisons takes a degree of freedom. If we compare this one to this one, and it's significantly higher, and this number is higher than this number, and this number is higher than this one, there's only one comparison we need to make to know, yep, this number is significantly higher than all these others. So instead of making 3 comparisons here, we can just make 1 and say, yep, this is higher. That same kind of, conceptually, that same kind of idea is what applies to Helmert coding, that if you're able to look at a group and say, yep, this is significantly higher than all the ones below it, And then you go down to the next level and you can say, yep, this is significantly higher than these down here. You already know that those implicit comparisons have been made logically if things continue in that pattern, if that makes sense. So yeah, so whenever we're doing, so that's what that helmet will do. It compares each level to all of the previous levels, or each level to the upcoming levels sequentially. All right, so for today's exercise, what we're going to do is researchers are interested in the relationship between different types of treatment, cognitive behavioral therapy plus medication, just CBT or essential oils, and their effect on well-being. And so they randomly assign some people to 3 different treatments or control groups. We have 4 groups total. The only variables that we're using is group and well-being. What y'all have in your scripts, what I posted was originally this, but I realized that I did that the wrong way. What I actually want is this. So conducted analysis, that what they want to compare is CBT and meds versus all the others, CBT versus essential oil and the control, and the essential oils versus the control. And see, like, does is that CBT plus medication better than all the other options? Is CBT better than the essential oils and the control? And is essential oils an effective treatment compared to the control? What's that? What?
The curving line right there.
Next to the old constraints,
Yeah,
the old comparisons,
the dot or the dashed.
the dash.
This? How did I do that? It's just like
So more than kids, but.
it's just like slashes and I don't know what it's called, but like the shift / thing. But whenever you make it into a comment, it kind of slants it a little bit.
I was kind of wondering that too, but I didn't really care as much.
Oh, okay. Throwing it in the bush.
I mean, I'm agreeing with you.
We all have our priorities.
It was interesting, but I have a limited amount of resources.
I have ADHD, so something like that throw me off for the day.
Rest of your mix, they're talking and it's distracting.